Hi everyone. In this video, we are going to discuss about Norton's theorem. The main objective of Norton's theorem is used for circuit analysis simplification and to study circuit's initial condition and steady state response. Right? So let us see the statement of Norton's theorem. See, Norton's theorem states that any linear bilateral active network containing voltage sources, current sources, and resistances can be replaced by a single current source in parallel with a single resistance. So here a single current source is Norton's equivalent current and single resistance is equivalent resistance across AB terminals. See, where the Norton's equivalent current IN is the short circuit current through the terminals AB and resistance Rn is equivalent resistance between the terminals AB, right? So here, simple thing. So as per the statement, any linear bilateral active two-terminal network can be replaced by single current source in parallel with single resistance. So in case of Thevenin's theorem, that entire network can be replaced by single voltage source in series with single resistance, right? So in case of Norton's theorem, that entire network, entire complex network can be replaced by single current source in parallel with single resistance, where single current source is short circuit current through the terminals AB and single resistance is equivalent resistance across the terminals AB, right? So I'll explain the procedure of Norton's theorem through numerical. Let us move on the procedure. So this is the numerical. See, so here in this numerical question is determine the current flowing through 2 ohm resistor using Norton's theorem in the circuit below. That is the question. Right? This is the circuit diagram. Okay. Now here in the circuit diagram, question is find the current passing through 2 ohm resistor. So this is the question, right? This is the network. Now here, uh, step 1 is remove the required branch through which current is to be formed. What is the step 1 here? Remove the required branch through which current is to be formed, right? And mark the terminals AB. That means here, what is the required branch here? As per the given question, current passing through 2 ohm resistor using Norton's theorem. That means that 2 ohm resistor, current passing 2 ohm resistor is the required branch, right? So we have to remove this resistance, right, from the given network. That is our step 1. Simple, similar to Thevenin's theorem. Okay, similar to Thevenin's theorem, here we have to remove the 2 ohm resistor branch from the given network, right? So this is the step 1. See, remove the required branch through which current is to be found and mark the terminals AB. See, so this is the given network, right? Now remove the 2 ohm resistor from the given network. See, and mark the terminals AB like this. Okay, here 2 ohm resistor is removed. In this 2 ohm resistor is removed here. Okay, so this is step 1, step number 1. Now step number 2, we have to short circuit the terminals AB and find current through it. That is step number 2. Step number 3, find the equivalent resistance across AB terminals. Okay, step number 4, short circuit current is current in parallel with Norton's resistance. Step number 5, connect the removed branch across the terminals AB and find current through it using current division rule. That is the procedure. I'll explain each and every step. Observe carefully. So this is step 1. Let us move on to step 2. See. So what is step 2 here? Short circuit the terminals AB. So these are terminals. So AB, short circuit these terminals. So what is step 2 here? Short circuit the terminals AB and find current through it. And denote it as IN, that is Norton's equivalent current or short circuit current, that is IN. Okay. So what is step one here? Remove the required branch through which current is to be found and mark the terminals AB. What is step number two? Short circuit those terminals, short circuit the terminals AB and find current through it, which is denoted as IN or ISC. That is short circuit current or Norton's equivalent current. Right? Now see here. So this is the modified diagram. This one is modified diagram. Now see here. So here, now we have to calculate the current passing through IN. That is the current passing through AB, not IN, current passing through AB, this one. Okay. So for that, for calculating IN, here number of techniques are there. Earlier, we have discussed KVL, KCL, mesh analysis, nodal analysis, source transformation technique, right? Thevenin's theorem, number of techniques are there. Okay. Na? Here, now in this example, I applied mesh analysis. Okay. So by using mesh analysis, I have to calculate the current passing through terminals AB. Of course, if you want to apply nodal analysis, you can apply whatever technique is there. Okay, you'll get same answer. You can apply any technique. Okay, answer will be same. Okay, so here I apply mesh analysis. So as per mesh analysis, okay, so this is first mesh current I1, second mesh current I2, right? So according to KVL, Kirchhoff's voltage law, first mesh equation is, so here current enters negative terminal of 100, that is 100 minus 100 plus 3 into I1 plus 5 into I1 minus I2. Okay, so from that we get this equation 100 equal to 8 into I1 minus 5 into I2. Okay, earlier we discussed this mesh analysis. Okay, so that's why I don't go in depth. So 100 equal to 8 into I1 minus 5I2, right? This is equation 1. Let us consider mesh 2. Okay, this is the mesh 2. So here mesh 2 current is I2. So as per Kirchhoff's voltage law, so here I2 enters 5 ohm resistance, that is 5 into I2 minus I1 as per mesh analysis technique. So here 7 into I2, okay, is equal to 0. That means from that we get minus 5I1 plus 12I2 equal to 0. Okay, so if you have any doubt in mesh analysis technique, kindly go through my mesh analysis technique video. So definitely you'll clarify each and every doubt in that. See, this is the mesh 2 equation. Minus 5I1 plus 12I2 equal to 0. This is a mesh 2. This is mesh 1. Now solve these two equations. Solve equation 1 and 2. Then we get I1 and as well as I2. So this is I1, 16.90 amperes. This is I2. Okay. Now, as per the given circuit diagram, as per this diagram, okay, as per this diagram, so here, as per this diagram, here I1 is this one. Now, what about I2 here? What about I2 here? I2 equal to IN. That means relation between I2 and IN is equal. The reason is here. What is the mesh current here? I2 is the mesh current. Okay, current passing 7 ohm resistor is I2. So here I have to calculate current passing through AB. That means I2 equal to IN here. So that is your Norton's equivalent current. Very simple. Norton's equivalent current. So this is the procedure to calculate IN value. Of course, for example, if you want to calculate IN value by using nodal analysis, then so I first identify the number of nodes. So this one is node 1. This is node 2. Okay, node 2 should be grounded. As per node analysis technique, node 2 should be grounded. Now assign variables to the nodes, okay, whose voltages are unknown. That means here V1 voltage, here V2 voltage, but V2 should be 0. V2 should be 0. And after that, write node equation at node 1. What is the node equation here? So what is our assumption as per node analysis technique? I1 plus I2 plus I3 equal to 0, right? At this node, all currents are leaving. So I1 plus I2 plus I3 equal to 0. So what is I1 here? V1 minus 100 by 3, V1 by 5, and V1 by 7. So from that, we will get V1 value. Okay. So once V1 is obtained, then we need to calculate current passing through 7 ohm resistor. That is your IN. Okay. So IN equal to V1 by 7 ohm resistor. So that is the procedure to calculate IN by using nodal analysis. Okay. You can use any technique. Answer will be same. Now, let us move on step number 3. See, this is the step number 3. Now, what is step number 3 here? Replace the independent sources with their internal resistance. Right? This step is similar to Thevenin's theorem. Replace the independent sources with their internal resistances. Okay, that means here, so here as per the given network, as per step number 1, remove the required branch and mark the terminals AB. Right? So at those terminals we have to calculate equivalent resistance, that is your RN, Norton's resistance. So now here, so according to parallel operation, parallel connection of circuits, it means parallel connection, assume some current flow at terminal A. That current is divided into two parts. Whenever current is divided into two or more number of parallel paths, that circuit is said to be parallel. That means here these two are contained parallel. And before that, see here condition is replace the independent sources with their internal resistance. That means here this voltage source must be replaced by its internal resistance. That is short circuit here. If any voltage source is there, that should be short circuited. If any current source is there, that is open circuited. Okay. Now, so step number 4 is calculate RN value. Calculate Norton's equivalent between the terminals AB. So for that here procedure is, so assume some current flow. That current is divided into two parts. Okay. Then whenever current is divided into two or more number of parallel paths, the circuit is said to be parallel. So 3 and 5 resistance are connected in parallel. This parallel combination is connected in series with 7 ohm resistor. That is the meaning. So here 3 parallel 5 plus 7. Okay. Now see. So 3 parallel 5, 3 parallel 5 means, what is the parallel combination of 3 and 5 means? As per conventional procedure, 1 by Rn equal to, or 1 by R equivalent equal to 1 by 3 plus 1 by 5. But a shortcut method is product by sum. Parallel combination of 3 and 5 is product by sum. So 3 into 5 by 3 plus 5. So 15 by 8. Okay. So here 15 by 8, that combination in series with 7 ohm resistor. That is your Norton's equivalent resistance. I'll show you those calculations. See, here Rn equal to 15 by 8 plus 7. Okay, this is Rn. Rn equal to 8.875 ohms. Simple. Right, this is Norton's resistance. Right. Next, step number 5. Connect IN in parallel with Rn. In case of Thevenin's theorem, step number 5 is connect VTH in series with RTH. So here IN in parallel with Rn. So this is Norton's equivalent current in parallel with Norton's equivalent resistance. This is step number 5. Right. Next, let us move on step number 6. See, step number 6 is connect the removed branch. What is the removed branch here? What is the removed branch here? I'll show you. So your removed branch is from the given network. Removed branch is, I'll show you that, and only I'll get more clarity. See, so here 2 ohm resistor is removed branch. 2 ohm resistor is removed branch. Now here connect the removed branch across the terminals AB. Connect the removed branch across the terminals AB, right? Or across Norton's equivalent circuit, right? I'll show you that. Right, now see here. See, connect the removed branch between the terminals AB and find current through it using current division rule. Of course, by using any technique, you can calculate the current passing 2 ohm resistor by using any technique. Not only current division rule, but current division rule is best method. Okay. So here, this is the Norton's equivalent circuit, IN in parallel with Rn. Right. Right. Now connect the removed branch, connect the 2 ohm resistor across the terminals AB. That is the meaning here. Okay. So here now, what is the main objective here? Find the current passing through 2 ohm resistor. Okay. So for that, for calculating current value, so apply current division rule. So what is the current division rule here? Total current, that is input current into, that is 7.04 input current into, so opposite resistance of required branch resistance, that is 8.875. This is the opposite resistance of required branch is 2 ohm resistor. So opposite of this is 8.875. So 8.875 divided by sum of total resistance in parallel circuit. These two are connected in parallel, right? Sum of total resistance in parallel circuit. So 8.875 plus 2. That is our final expression. So I equal to 5.745 amperes. Okay. Again, I would like to remind you the procedure of Norton's theorem. Here, statement of Norton's theorem is, so any linear bilateral network, right, can be containing voltage sources, current sources, and resistances can be replaced by single current source in parallel with single resistance. Okay, where single current source is short circuit current through terminals AB, and single resistance is equivalent resistance across AB terminals. Okay, so procedure of Norton's theorem is, so step one is remove the required branch through which current is to be found, and find and mark the terminals AB. That is step number one, right? Step number two. Step number two, calculate short circuit current through the terminals AB. Okay, that is step number two. That is your Norton's current. Step number three. Okay, so replace all the independent sources with their internal resistances. If any voltage source is there, short circuited. If any current source is there, open circuited. Right. Next, step number four. Calculate RN, that is Norton's equivalent resistance across the terminals AB. Right. Step number five. Connect IN in parallel with RN with output terminals AB. Step number six. Connect the removed branch across the terminals AB and find the current through it by using current division rule. Right. Thank you, one and all. Bye, everyone. Have a nice day.